ready to start today. We're very happy to have Netta Engelhardt, who, as you see, will be telling us about spoofing entanglement in holography.
Very much, Juan. Thank you for the invitation. Thank you all for coming here today, even though this talk was supposed to be on Monday. I was sick, and as I was saying earlier, I still can't really hear out of one of my ears, so the infection traveled into my ear. So I might ask people to repeat themselves one or two times. Sorry about that in advance. Okay, so this talk is based mostly on a paper that appeared in July with 4 of my collaborators. My former student, Austin Foxted, who's leaving MIT to go to UC Davis for a postdoc. Adam Levine and Abita Verheiden were postdocs at MIT. Adam used to be here, and my student Lisa Yang. So I'm going to begin with some motivation. Now, I realize this is a pretty mixed audience. Some people come from the CS perspective, some people come from high energy theory. I'm going to try to straddle the divide in this talk. So that means that there's going to be parts of the talk that are going to be boring for everyone. Hopefully not for everyone at the same time, though. So in advance, if you see something like, oh, I've seen that a million times before, feel free to just tune off until the next thing that you haven't seen comes up. But I am a high energy theorist, and so the primary motivation for this is always going to be understanding something in gravity. So I know that spoofing entanglement is something that has come up a lot in the context of computer science for various reasons. The computer science folks are interested in understanding the phenomenon of entanglement spoofing. I am not going to go at all into the motivations, the computer science motivations for why this is interesting. If you know those motivations, that's great for you. If you don't already know them, then maybe you're more interested in the gravitational motivation anyways. So I'm going to talk about why I care about understanding entanglement spoofing and why we want to study it in the context of holography. So why this is context and background. So why do we study entanglement spoofing from the perspective of gravity? Version. Now, before we get into that, what do we really mean by entanglement spoofing? That's something that's going to come up in progressively more rigorous detail as I go through the talk. At a very heuristic level, just for context and motivation, essentially it's a phenomenon where you have a state which looks like it's very highly mixed, but actually is fairly close to pure. So those of us who are interested in gravity are probably already thinking, I know an example of that. That's what the evaporating black hole looks like. So one reason why we might be interested in understanding this phenomenon in gravity is that it comes up in a very natural context, which is the black hole that's evaporating. So one reason is that we see this happening in the context of the evaporating black hole. So in the context of the evaporating black hole, we have this very famous diagram of the entropy of the radiation as a function of time. And we know that according to Page, the curve goes up and it comes back down. But according to Hawking, I should have drawn Hawking first. According to Hawking, the curve sort of asymptotes and eventually plateaus to a constant value. The entropy does not come back down, whereas according to the Page curve, the entropy does come back down because the radiation purifies. So naively, no one's going to hold me to this curve being actually accurate. Now, naively, this calculation is the naive calculation that we do, that the state looks like it's highly mixed, state of the radiation, but we know that secretly the state is actually purifying as we go past the Page time. So this is an example of a situation where we have a state, so this is the Hawking curve, this is the Page curve. And so in this situation, it looks like there's a naive calculation in which the state of the radiation looks like it's highly mixed. Here, it's actually purifying. So this is an example of the phenomenon of entanglement spoofing. Whether this matches word for what the CS people would call entanglement spoofing is going to be part of this talk, because this means something very precise in computer science language.
The
Now, this feature of
is the
entanglement
difference between Boltzmann entropy, let's say, or coarse grain entropy and fine grain entropy?
Yeah, so I'm gonna be talking a lot about coarse grain versus
Okay.
fine grained entropy. I would say that the naive Hawking calculation, it thinks it's computing the fine grained entropy, even though it is actually secretly computing, of course, a coarse grained entropy. If it is still a von Neumann entropy, it's just the von Neumann entropy of a coarse grained state. So I'm gonna, I'll get into more detail about what the Hawking calculation is actually doing. So I'm gonna spend a little bit of time actually talking about this in much more detail. This is sort of just more of a little bit of context. But this is intended to be, it is important, I suppose, that we do think that, but we used to think that the Hawking curve is computing something that looks like a von Neumann entropy, even though we knew it couldn't really be because the von Neumann entropy had to come back down. Okay. So one thing that we might want to understand, so this is a very, the hallmark feature of the black hole information problem. And there are a lot of things we've understood about it recently, some things that we might still want to understand, some questions that we might want to ask. For example, about the dynamics of evaporating black holes. So the dynamics of the evaporating black hole is a unitary dynamics that take a state which does not look like it spoofs entanglement and creates a state that does spoof entanglement. So these are unitaries that generate entanglement spoofing states. And we might want to ask what kinds of unitaries can do this? How general is this phenomenon? What are the properties? What are the class of unitaries that describe black hole evaporation very well and the process of the way in which the radiation gets out? So this is something we might want some more clarity on and might want to study the phenomena of entanglement spoofing to understand how it can be generated dynamically. Now, another question we could ask is about uniqueness of black holes in this category. Sorry, can everyone still read this before done? So we might want to ask, are black holes the only gravitational phenomena that can generate entanglement spoofing states? So is this something that's unique and special to black holes, or is this something that other gravitational phenomena can also cause? So are black holes the only gravitational phenomenon that can spoof entanglement? If not, we could ask whether there's some kind of an analog of the information paradox for something that's not a black hole. So these are two questions that we might want to answer about black hole evaporation that would require us to understand how entanglement spoofing works in the gravitational context. Now, when I get to the end, hopefully I will get to the end, I'm going to discuss potential answers to both of these. I'm not going to answer this one, I'm just going to speculate a little bit. This one, under the assumptions of this paper, we can actually answer in the affirmative. Black holes are the only phenomena that can generate pseudo that can spoof entanglement. Yeah.
Okay, I'm a little confused about number two. Like, is it like that they do it the best, or that they're the only thing?
So
Is this
when I
the
say
only thing that
gravitational
can do it from
phenomenon,
computer
I
scientists,
mean,
not?
good. So this means that they have to generate, I guess you could say they can spoof a large amount of entanglement, but a gravitational amount of entanglement. So that's what I mean by gravitational phenomenon here. So it's a gravitational phenomenon, it has to source a gravitational amount, meaning order 1/g.
Oh, thank you.
Say order 1/g amount of entanglement. Okay, so again, I'm going to address these two or discuss these two at the very end. There is another motivation for understanding entanglement spoofing that doesn't come from black hole evaporation, and that's the connection between entanglement and space-time emergence. So in a situation where we have what I like to call a classical space-time, meaning if you have order 1/g entanglement between two subsystems, then you have a QES with non-trivial area. So in other words, you don't have a situation where the leading order area piece is order one over, the leading order entropy piece is order one over G, and you don't, and the area is the empty set.
I'm
So for
sorry, I have
classical
no
space-
feeling what it means to have one over G entanglement.
So was it?
I have no idea what it means to have order one over G entanglement. What should I be saying?
So if you want to think purely in terms of the boundary theories, we just talk more, without gravity, then this scales as n squared. So you can think of this, you can think of this as scaling the log of the dimension of the Hilbert space.
The space of the boundary or the space on its?
So I mean, this is the only parameter we really have in the gravitational theory to play with. So I mean, this is in some sense you can think of this like the entropy of the black hole. Which is not exactly a quantum mechanical way to, I mean, it's the only parameter you have. It's not the dimension of the Hilbert space. It just has to be large enough.
That's O1 over G. Okay, I imagine this is a small number, right?
So order one over G is a very large.
Oh, that's very large.
G is a very small number. One over G is going to be a very, very large number.
So it's supposed to be
So
mostly
in the
pieces of
classical
Hilbert
limit, in the limit where we just have quantum fields on a curved background, that's the limit where G goes to 0.
So if you say order one over G, you mean most degrees of freedom are entangled or very few?
Most right?
If you say order one over G entangled, do you mean most degrees of freedom are entangled or very few?
I mean, this is as entangled as something can get in ADS.
That's good, okay.
Yeah.
Thank you.
Yeah, order one over G. Okay, good. So for classical spacetimes, and again, what I mean by that is that if you have order one over G, entanglement, there's a non-trivial QES. So there are some counterexamples to this when you have the evaporating black hole and you do a canonical purification. I'm just going to ignore that. In this context where you don't have to worry about that, then it appears to be the case that entanglement builds,
What does QES stand for?
just 1 second, space-time bridges. Yeah, what was the question?
What does QES stand for?
Quantum extremal surface. So this is the semi-classical analog of the Ryutaki-Yanagi surface, which is the surface in the bulk that computes the von Neumann entropy of the boundary theory. It's the ADS-50 dictionary for the von Neumann entropy of the boundary. Okay, so in this situation, it seems that we have a connection between entanglement. Entanglement builds space-time bridges and space-time conductivity. And you could say, well, if entanglement builds space-time, well, what does entanglement spoofing generate? So a question we could ask is to say, okay, what is the space-time avatar of entanglement spoofing?
Will you define entanglement spoofing?
Hmm?
Will you define entanglement spoofing?
I haven't defined it yet.
Oh, okay.
I said it vaguely. It
Okay.
means when you have a state that looks mixed, but actually
Okay,
is
fine.
much less mixed than you think. I'm gonna define it
Okay.
shortly. Yeah, but essentially the end, what we find here is that it does build some amount of space-time, but not a full space-time bridge. Essentially, it builds a Python's lunch. So you have more space-time than you might naively have thought, but not so much that you can actually connect the two boundary regions to each other. Okay, so then 1, 2, and 3 are kind of the motivations here, and I'm going to try to get to addressing them at the end. But for now, I do need to make some things precise, such as what does entanglement spoofing even mean? What do we mean by that in a gravitational context? And for that, it's going to be very helpful to study the evaporating black hole, because there are various notions of entanglement spoofing in computer science, various requirements, indistinguishability with respect to various things, being equipped with various types of advice, and we have to figure out what's the right notion to capture what we think of as interesting in gravity, which is in some sense guided by the evaporating black hole. So I want to look at a case study of the evaporating black hole in a little bit more detail, which will help us define things more precisely for gravity. Okay, so I'm gonna work with the usual setup. We have a black hole in ADS. It's evaporating dynamically into a bath. I don't especially care whether it's single-sided or two-sided. Maybe single-sided for simplicity. So the QES, the original QES is just the empty set. So here we have coupled it dynamically to a bath at some point. So this is just the usual story of the evaporating black hole. I know many of us have seen this and nauseating the large number of times, so I'm going to try to not go into it in too much detail. The only relevant points that I want to discuss here are the two crucial things that go into the page curve calculation. So that's the evolution of the quantum extremal surface. So before the page time, the quantum extremal surface of the radiation, we have a single-sided black hole, it's just the empty set. So the QS equals the empty set. And then after the page time, there's a switch over on dominance, and we have a new QES, which is very close to the horizon. Of course, the old QES still exists after the page time, but now it's subdominant. It's no longer the minimal quantum extremal surface. So in computing the von Neumann entropy, we use the new quantum extremal surface. Now, the crucial point for us is the change in the entanglement wedge. So before the page time, the entanglement wedge of the radiation is literally just going to be the domain of dependence of a slice here of the bath. And then after the page time, it includes the black hole interior. So there is a jump here, and we can see, this is a single-sided black hole. And so we can see that if we had made a mistake and used the same quantum extremal surface before and after the page time, we would not have known that the state is purifying, because we would have thought that the entanglement wedge of the radiation was this, and then became that. And we wouldn't have gained any knowledge of the fact the state is purifying. Another way to put this, if we had made the mistake of using the non-minimal so-called outermost quantum extremal surface, empty set in this case, we would have recovered the Hawking curve instead of the page curve. So the crucial ingredient here is the page curve is obtained from the minimal QES, regardless of whether it's outermost or not. And the Hawking curve is obtained by the outermost QES, regardless of whether it's minimal or not. And so the mistake, the spoofing here is facilitated by the fact that there are two candidates for the dominant quantum extremal surface. And if we're not smart enough to know that this is the minimal one, then we're going to think that this is the one that we should actually be using. And so the spoofing here, the difference between these two curves is the difference between using the minimal and non-minimal versus outermost, say, QES. Now, we'd like to turn this into some concrete notion we can use to define entanglement spoofing. And to do this, we have to ask, what does it mean to use the outermost QES in the boundary language? Fortunately, there exists already a dictionary entry that we can use to understand this better. So this is the so-called simple entropy / outer wedge dictionary. And this is what tells us what is the boundary dual of the non-minimal quantum extremal surface, the outermost quantum extremal surface, and its candidate for the entanglement wedge, which we call the outer wedge. So the wedge of the outermost QES out can denote it's called the outer wedge, WO, can be reconstructed, or rather is the dual of a coarse graining. This might be, of course, be new. It had to be a coarse graining because somehow we have to forget about everything that's in the entanglement wedge, but not in the outer wedge, right? The outer wedge is nested inside of the entanglement wedge. And so there has to be some kind of a coarse graining that discards everything that's in the entanglement wedge, but not in the outer wedge. And this coarse graining discards all of the high complexity data in the state, essentially. It discards the exponential, or I won't be super careful about the difference between exponential and super polynomial. The important distinction for me will be between exponential and polynomial. So exponential complexity operators. And the way that we can accomplish that is using the following coarse graining protocol. The generalized entropy of the outermost QES is given by a maximization protocol over all states in some set H, which I'll define in a second, the von Neumann entropy. And this is the von Neumann entropy of what we call rho simple. Where H is the set of all states rho that agree with the actual state on the expectation values of polynomially complex operators.
So is this the Hilbert space of the radiation, or is it?
This is, so this is general, it's completely general. Now, if we wanted to apply this to the radiation, this would become the empty set. And this essentially would give us back the Hawking state.
But so where do you want to apply this to? In order to get the,
So what I want is to, so what I'm trying to get at is a good definition of entanglement spoofing.
right,
And to do that, I want to and that has to capture this difference between the Hawking curve and the Page curve. This is the handle we have on understanding that.
but in your picture, I just want to understand what rho is a state of the CFT.
Oh, so psi here, yeah, psi here would be the state of the radiation for in our,
Yeah,
yeah,
so
yeah,
yeah.
that's right, yeah, the actual state of the radiation. Yeah, Edward.
Is this definition supposed to make sense exactly or only in perturbation theory and Monogram?
This is perturbation theory monograph, definitely. Exponential expectation values of poly. Okay, now, so there's essentially what this is saying is that you can reconstruct the outer wedge if you have access to polynomially complex operators. There are various different ways of justifying this. A fairly simple one is that you say, okay, let me consider a situation where my causal wedge has as a bifurcation surface, the outermost extremal surface. That's a very non-generic situation. Then I can reconstruct everything in the outer wedge using one-point functions. That's very simple. Now, suppose now that I'm in a more generic situation where my quantum extremal surface is not the bifurcation surface of the causal wedge. The only way that that's the case is if I have some stuff falling across the horizon. So that's a situation where I have a QES, the outermost QES. The only way that this bifurcation surface is not extremal is if there's some stuff falling across the horizon and coming out of the past horizon. And so what we can do is we can do HKLL reconstruction up to here. That allows us to figure out what stuff is falling across the horizon and what sources correspond to it on the boundary. We turn those sources off. The horizon moves inwards a bit. Then we repeat this protocol, and you can prove that you can do it all the way up, prove at physics level of rigor, you can do it all the way up to the quantum extremal surface, the outermost quantum extremal surface, but no further. So this is a way of justifying why these simple operators are things that you can use to reconstruct everything in the wedge of the outermost quantum extremal surface. Okay, so back to the story that we're most interested in here. Any questions so far about this dictionary entry?
I have a question. So if we look at the JT gravity with some heavy orbiter inserted, the equilibrium path and prepare some non-wormhole state. In those cases, we have a bifurcation, but there's no matter going in and out. So, and by that case, you have a long worm.
So I believe that if you're talking about a situation where you have some stuff behind the horizon, you introduce some heavy operator or something that's like a shell behind the horizon, then normally the bifurcation surface is extremal in that case.
No, it's not. So it's like we prepare the state, like insert some heavy operator on the equilibrium path, not some shockwave. So in that.
Sure, but I mean, my point is that the only way for the horizon to not have, okay, you can have an empty set QES, which is not what happens in JT. Or you can have a situation where the, you have to have some value, some diligent flux across the horizon in order to have a non-vanishing expansion. That's the only way you have a non-vanishing expansion. And as long as you have something like that, then you can turn off the flux.
Oh, okay.
I have a question about this.
Yeah.
So if this matter that falls in is a mixed state,
Yeah,
can you remove it?
sorry, you're talking about a quantum, so when these are not classical sources, but quantum sources?
Well, let's say it's a particle that is in a spin half qubit that is in a mixed state. So if I want to remove it, I will need to know what's in it.
Yeah, so-
And so on, and
Yeah,
that
so
sounds like I will need some exponential complexity.
Right,
That's why I'm
that's a very good question. So there is a subtlety here that comes up as soon as you allow yourself to consider back reaction from quantum effects. And that modifies this prescription in the sense that now you have to start worrying about what state, what is the state for the you have to give this prescription for the maximally mixed state in your code subspace, which in this case, this prescription still works. At the level of this talk, I'm going to be working in a minute on the state that assumption. I'm going to be working with quantum fields on a curved background with no back reaction. So that subtlety won't come up, but you do have to modify this prescription as soon as you will consider a situation where maybe, you have some entanglement across the horizon that you're breaking in some way. And then you have to consider large back reaction from quantum effects. So I can discuss that towards the end. Sorry?
If it takes you away from your.
Yeah, I can discuss that towards the end. It's one of the reasons that we choose to not include back reaction for now, because it makes the prescription more complicated. Most likely still works, but it's just the whole thing becomes a lot more complicated. All right. Okay, so we're interested in entanglement spoofing, meaning we're interested in the relation between rho simple versus the state psi, which is the actual state of the system. So when there's a large entanglement gap between them, as we have, in this case over here, that's when we have something that looks like we might be looking at entanglement spoofing. So now we have to get into the details of what we mean by entanglement spoofing based on this intuition of what the page curve and versus the Hawking curve are computing and what do we want to mean by spoofing entanglement in ADS CFT. So we want to have these two states that have so we want some kind of an entanglement gap. Between these two states. We also want the states to, in some sense, be indistinguishable to high complexity, to low complexity operators, right? There's a sense here we say, okay, if you can only do simple things, then you can't tell the difference between these two states. So we want something like indistinguishability between these two states. And I say indistinguishability, I mean to simple algorithms, not to arbitrarily powerful algorithms. This is a bit of a nuanced term, and I'll get to it in a second. And the final thing we want, because we'd like to stay in the semi-classical limit, is that these states can be efficiently prepared, meaning it doesn't take you an exponential time to prepare these states. I only want to worry about classical and semi-classical things.
So
use the term efficiently preparable to denote that. Now, indistinguishability is something that's a little bit subtle. It's a somewhat nuanced concept. You could say, okay, I want my simple algorithm to not be able to distinguish between these two states, but what does that mean? What does my algorithm get access to? Does it have access to arbitrarily many copies of the states? Does it have access to advice? Does it know what row simple is and what psi is, and I hand it some arbitrary, it's some state it doesn't know, and it's told to tell which one it is? You need to figure out what is the notion of indistinguishability that's appropriate in this context.
Can you repeat again what what these states are on? Is this the Hawking radiation?
Yeah, so for the Hawking state, so this is the actual state of the radiation and when it purifies and gives you the page curve.
So this is like way post page time when we
So
have
this
the
is,
pure
so
state.
I'm using psi, I guess, to refer to the state as also a function of time, but this is the state it computes at any moment in time it follows the page curve. And row simple is the state that follows the Hawking curve, is obtained from the page curve, from the actual state by this coarse graining protocol.
So psi is still mixed, just not as mixed as we.
Yes, and
I
that's
see.
an excellent point you bring up now, because now we're gonna say, well, if psi was pure, if we're sort of, or close to pure, if we're at the very end state of evaporation, then if we have access to 2 copies of psi, we can do the swap test, and we will know that psi is not row simple. We will know that it is purifying. In fact, if you even have access to just 1 copy of the state, but you have access to advice, so you're given row simple and psi, then you can also do the swap test and tell with very high probability, probability essentially 1 if you're after the evaporation is finished,
What kind of
that the
advice?
state is not mixed. Sorry.
What kind of advice, meaning the actual?
So the advice I'm
knowledge?
talking about is just that the algorithm is given row simple and is given psi, and then it's handed some state chi, and it's told determine if this is row simple or psi.
So then you still have 2 copies of psi.
So then you basically have 2 copies, exactly. So that's essentially like allowing you to use the swap test. So now if we're talking about times that where you have more than a scrambling time left in the life of the black hole, then you actually can't use the swap test anymore. I mean, the probability is that it succeeds is not greater than 1/2. If you have if you have less than a scrambling time left in the black hole, the probability isn't 1, but it becomes progressively larger than 1/2. So we're going to try to stick to times that are very easy for us to understand semi-classically. So when there's an order 1 fraction of the black hole remaining, and in that case, we expect that even if you give the algorithm 2 copies of the state and advice, or multiple copies of the state, it still can't tell the difference between row simple and psi. So the expectation, and it's just an expectation that is hard to justify, but the expectation is that when there's an order 1 fraction of the black hole remaining, even access to multiple copies, as long as that number doesn't scale with n, access to any constant number of copies doesn't facilitate distinguishing. So the expectation we're gonna have for what we mean by entanglement spoofing, what we want is we want to have an entanglement gap which is large enough that we have some order 1 over g. You can see that it goes to infinity and g goes to 0 limit. Maybe even larger than that in the sense that we might want one of these to have extremely small entanglement and one of these to have in the sense of subleading in g and one of them to have leading order in g. We want indistinguishability even with access to multiple copies and advice. And we want them to be efficiently comparable. So this is what we want from gravity. Yeah, question.
Are all of these expected also say I take like just 2 disjoint intervals in the vacuum of a CFT? And you have 2 different extremal surfaces that compete, but is it the same story or do one of these fit?
So, well, for now, I don't want to worry about cuts across a boundary. I would like to consider full boundaries because as soon as you have cuts across a boundary, they're always going to match the leading order divergence. And so, because that's just, the UV behavior of the theory. So everything I'm gonna talk about here will be entanglement between two complete boundaries. There's a version of pseudo entanglement which involves an all cuts pseudo entanglement, which is just not going to work in holography.
So there's no like subtracted.
So sorry,
There's no like subtracted UV divergence in this plot. then?
no, so I'm not talking about that at all here, yeah. Okay, so,
May I ask you something? So from an abstract point of view, if I abstract, then I can look at the problem that you write on the right. So there are like two systems, A and B, then there is a state defining these two systems. This is the psi. And then there is another state which is rho, that is a mixed state. And these are the ones that we'll have to have with respect to this cut different entanglement properties. And so by the entanglement, you define just as the entropy of the reduced state. No, because for mixed states, we define entanglement in different ways, but you define it as entanglement of the reduced state.
Let me ask a question
What
which
is
is
the
related.
statement?
I think when you use the word entanglement, would you have used the word von Neumann entropy?
Yes.
And
Okay,
you're
I see.
always
Okay,
talking-
okay, so von
I think
Neumann-
she's always talking about.
Okay.
Always talking about the
Okay,
two
sorry,
sensitive
interests,
Yeah.
the same system, she has only one system,
yes,
and it's the von Neumann
Yes.
entropy.
Clarify, the state rho is only on one system, right? So I could think of purifying it, and if the entropy is high, then I would be highly entangled and otherwise not.
yeah, that's it.
Okay, so there is no second system. We're not
Yeah,
thinking
that's
about
right.
it.
There's always gonna be, there's always gonna be one system,
Okay.
the black hole and the
Von
region.
Neumann entropy.
And
or
yes.
entropy
No,
gap,
no,
People will, that's clear. The other question is, so in this setup that I mentioned, how do you translate that on one fraction of a black hole remains?
So
Do you know one system is much smaller than the other one, or what do you mean by?
this is when the two systems are comparable in size.
Okay.
And again, these states are only on one part, right? There's the second part we never look at really, which is.
So I'm
the
never looking at
purifies.
this is just a way of saying how much of the radiation is left. It's really just, I mean, it's convenient to talk about it in terms of the black hole, but I really just mean the radiation, it's not so late that essentially we lose the semi-classical picture.
Okay, but these rho and psi just live on a single system, and we just talk about entanglement because we think it's entangled to something else, basically.
Yeah, I mean, we can talk about the purifier, if you like, in this case, the black hole, but that's I mean, I'm really gonna be interested in one system. I mean, I'm gonna give an example with EFIs, which I think will really clarify
What
for the
are
people who like to
EFIs?
think in terms of the,
I'm sorry, there's people here who are not from black hole backgrounds, right? What is it?
You'll define it.
so I will define it, yeah,
Just not helpful to mention it and not define it.
Ananda.
Yeah, when you say O1, like what is the parameter that you're measuring size in? Like what's the N here?
What's N?
Yeah, like
Um,
O1 means like you're constant in some.
So I'm using the entropy of the black hole. Or I mean, if you like, the important thing is G Newton for us, which is, it translates into, I mean, it's a power of N. I'm just gonna always take it to be N squared, even though.
What is it?
So that parameterizes the size of the Hilbert space. So I'm gonna be very precise about the size of the Hilbert space. I'm generally going to take it to be, it's gonna scale as e to the N squared with some prefactor.
Is there a lower bound we can put on the von Neumann entropy of the radiation in the actual state instead of saying that a black, like order one fraction remains?
I mean, yeah, it's an order one fraction of the entropy of the radiation, of the Beckstein-Hawking entropy.
Right,
So
so
we-
so maybe perhaps we could say that, or what this order one is the ratio of the von Neumann entropy of the simple and the psi state.
Yes, yeah, that's exactly right, yeah. Okay,
Oh, wait, sorry,
one last question, and then I'm gonna
Yes.
move on.
When you say efficiently preparable, like efficiently preparable in what model, like starting from what state and what operations?
Yeah, that's an excellent question, that I'm going to assume that there's some state that we, the vacuum, if you like, there's some state that we can start out from. And then we can efficiently prepare it with some preferred choice of gates. I'm not going to get into that essentially at all. I'm just gonna say that in gravity, we think we can prepare these like a time that doesn't scale exponentially with N. That's what I'm gonna, I could get into the weeds of this, but then I'd have to give up two of the sections of this talk, so I'm not gonna do that. Okay, let's have one more board here. Okay, so I'm gonna say one last thing, and then I'm gonna talk about the concrete construction in terms of EFIs and the precise things that we prove. So it seems to be the case here that the essential thing for spoofing entanglement is having two QES candidates. And I'm just going to quote a theorem by Brown, Berbian, Susskind and Pennington, that if you have two QES candidates, an outermost and a minimal, then you have a Python stitch. It's something you can prove from maximin. And so essentially you have some, this is on a spatial slice, you have some outermost QES, you have some minimal QES. Maybe this is the empty set, and between them, you have a Python's lunch, which is exponentially hard to reconstruct. And what we're gonna see is whenever we have various notions of entanglement spoofing, we have entanglement spoofing in gravity that coincides with different notions in computer science, we're gonna find that we always have a Python's lunch in the dual. And that's not surprising, given that we've identified these two QESs as being essential for understanding the phenomenon of entanglement spoofing.
Right, I thought it was a conjecture, not the theorem.
So this is, the conjecture is that it's exponentially complex in here. The proof, just to take maximin, is that there exists this bulge here.
Right. Is that thing supported by stress energy?
Supported by the stress, what do you mean by that?
Is a vacuum solution?
You can have vacuum solutions. You can certainly have vacuum solutions with like this. I mean, I don't know, but would you call it an end of the world brain a vacuum solution?
If it supports stress energy in the middle. No.
Yeah, so I mean, you can just take the thermofield double. And then you just put an end of the world brain behind the horizon. You have you have a bifurcation surface here. So that's the outermost one, and the innermost one is the empty set. And so you have a bulge. So I don't know if you would call this being supported by matter, but you can do something like this.
But the fact that it turns around. I think there's some,
The fact that it turns around, I mean, it's possible that there are solutions without end of the world brains. I guess I'm coming up short on it right now, but it's possible. I don't see a priori an obstruction. Just supported by gravitational waves or something.
If you have a long wormhole and a two-sided black hole,
Mhm.
if there's more than one QES, then from one side or the other is automatically a Python lunch.
Well, yes, there has to be a Python sledge between them.
Well, maybe I should say if there's more than one, then from one side or the other, the outermost one is non-minimal. That's what I was really trying to say.
Yeah, if the outermost one is not, I mean, if it's minimal, then you just don't have a description of the interior from one side, and then the other side contains all the way to the minimal one. So then one side will always have a lunch in that case, but yeah. Okay, so what I'm going to do is I'm going to prove that there are various that there are two notions in computer science that capture entanglement spoofing that coincide with our gravitational notion. And these both have Python's lunch in the dual bulk. But to do this, I need to state a couple of assumptions about what I'm going to take the bulk to look like. So the first assumption is about the fact that we have states on different geometries, right? So rho simple and psi correspond to different bulk geometries. And that means that I need to worry about the fact that I'm talking about two semi-classical states that are defined on Hilbert spaces of low energy perturbations of quantum field theory, but these are on different space-time manifolds. So I'm going to take the bulk Hilbert space to be a direct sum. Where each of these is the Hilbert space of low energy perturbations around some particular geometry G1 versus G2. And I'm going to assume that the algebra bounded operators on this also is a direct sum. Again, this is just quantum field theory in a correct background. This is all in the bulk. About the dictionary, I'm going to assume entanglement wedge reconstruction. And because I'm gonna be using a lot of computer science language, which is formulated in finite dimensional Hilbert spaces, I'm gonna have to work with, very, very careful about taking the large end limit. So I'm not going to subject all of you to how we do this, but I'm gonna try to be just a little bit precise about what my assumptions are. So this is essentially based on a paper by Faulkner et al., where they make it very precise on how to do entanglement wedge reconstruction as you take the large end limit. And in terms of quantum channels. So I'm just going to take entanglement wedge reconstruction to be the statement that for any two states in the algebra of the entanglement wedge. So this is the full algebra, and now I might take the entanglement wedge to be the wedge of one boundary, so I'm going to call that A. There exists a sequence of states in N, all these rho N, sigma N. So these are the boundary states. I will always put a little n there to denote the fact that we're taking a sequence as n goes to infinity. And let's see, for every, sorry, this should be, this is an operator, and this is the, sorry, this should be A here. Rho N, and boundary operator. This is a boundary state, boundary operator. AN, and these belong in the algebra that I'll call A sub n. Which is, this is boundary algebra, such that the limit as n goes to infinity of the expectation value of AN in rho n is the expectation value of A in rho. And in particular, these are related, the boundary state and operator are related to the bulk state and operator by a quantum channel.
So this n is the same n as before?
Sorry?
Is this the same n as before?
It's the same n as before,
Or
that's right.
number of qubits?
Yeah, and I'll call the Hilbert space, the boundary Hilbert space H sub n also to remind us that it's not the same as the bulk Hilbert space.
So the point of this is to work in the G Newton to zero limit. I guess.
So what's that?
The point of this is to be able to work in the G Newton to
Yeah, the
zero
point is,
limit.
and to be able to use various inequalities that are true with finite n and be careful about how we take the large end limit to make sure that
But
there's still-
the reason why you want to take the large.
So I'm not gonna be,
because
sorry,
you
I'm not
want to
gonna be
able
working
to
with finite
quantum
n, when I'm talking about the bulk ever. But I'm gonna be manipulating various things in the boundary as finite n and then taking the limit. And this allows me to take the limit in a way which is careful.
Okay, sorry, another question, like, why is there a direct sum in assumption one and not a tensor product, again, in this thing?
So the reason there's a direct sum here, I don't want these two interacting with one another in any way. These are just two bulk spacetimes. There's just quantum field theory living there. This is just the state of that quantum field theory. This is all in the bulk, not in the boundary.
But why you have two separate bulk?
Because I have one that's gonna be dual to the single state and one that's gonna be dual. to the
Oh,
vector
you
state.
have two things.
These are two different
Okay, oh, I
geometries.
see, I see.
Yeah, so these are really dimensional channel.
So why do we need a direct sum? Can't we just look at the two situations independently?
What do you say?
Why do we need the direct sum? I think we're at least the two of us are.
So the
convinced.
direct, I mean, the direct sum,
I could just look at
I need.
Sorry, wait.
I don't want to work, I don't want to deal with situations where I have fluctuating geometries and, I have things that operators that can somehow mess between my two different
But
geometries.
couldn't we then just consider HG1 and separately HG2? I mean, why do I have to make a direct sum of these
You'll
spaces
see,
and
in the
not
way,
look
the
at
way
both
that
separately?
we talk about operators that live on the direct sum, and it means it makes our, it facilitates various proof techniques for us to be able to talk about this as one single algebra.
But the algebra is also a sum, right? So I'm really actually.
The algebra
doing
is
things independently.
also a sum.
Is there a reason or is it just it doesn't hurt and it doesn't help?
Well, it turns out that if you don't do this, then you end up encountering various operators that you really don't want to be dealing with. So I'm not gonna get into the weeds of this because I am going to be out of time in 35 minutes and I haven't even started on this part yet, but this is somewhat essential for us to not have operators that are going to mess with the structure of the
I
geometries.
think this we all
So,
understand. The question is, why do we have to glue these spaces together? Can't you just keep the
No,
G1 space, move everything?
We
and then
can't
do-
because we're going to talk about operators that act on this full Hilbert space.
But the B is
I
also
haven't
some.
talked, you're gonna have to let me give that talk if you're going to want to hear it to see where they come up, okay?
Okay, but they will come up. Okay.
Okay, and then the final assumption, we'll finally start explaining new things. Is just formalizing what I said about the outer wedge. So we have some the algebra of AOW, which is the algebra of the outer wedge. And this is the algebra. The outer wedge. And for all A operators A that live in the outer wedge algebra, the dual boundary dual A sub n is polynomially complex in n, so the scaling with n is polynomial. And the converse of this is also true. So if you have a dual which is polynomially complex, then you have an operator which is polynomially complex, then its dual is going to live in the outer wedge algebra. And in particular, this implies that if the outer wedge algebra is a proper subset, the actual algebra is such. Okay, so without further ado, these are the assumptions. I'm going to go ahead and.
Is that the definition or is there a meaning of like?
Is there, sorry?
Is that the definitions or is?
This.
Yes.
Uh,
What's the definition
so-
of Python flash in this context?
It's not the definition, it follows from this theorem. So this just tells you that there exists something beyond the outer wedge. This tells you that that means there's a bulge.
How do we know that? Yes.
So if the outer wedge algebra is a proper subset of the entanglement wedge algebra, then the entanglement wedge is larger than the outer wedge, which means you have two QES candidates, which means that you must have a bulge.
Okay, so this is all these algebras are defined in the bulk. It's not an abstract algebra.
That's, yeah, so
Sorry,
whenever
I
something is
missed
defined
that
on the
in the
boundary,
beginning.
it
Sorry,
will have a
yes,
little
fine,
n
Fine.
next to it, yeah. Okay. All right. Okay, so first I'm going to tell you the main result we have about single state spoofers. So when I say single state spoofers, I mean what we've talked about so far, which is that you have a single state, a pair of states, and they spoof entanglement in this sense. Afterwards, I'm going to talk about ensembles, which is going to be a different story. So the main result. So geometric states. And what I mean by that is that in the large N limit, they have a dual bulk spacetime. So they have this relation in terms of the quantum channels to an actual bulk, to a dual bulk that exists in semi-classical. We're going to assume that these are K-copy indistinguishable. Where K does not scale with N. So for any K that does not scale with N.
Indistinguishable means completely or under efficient circuits or something?
Sorry?
Indistinguishable means completely indistinguishable or? under
No,
efficient
sorry,
circuits?
it's computationally indistinguishable, yeah. Copy. So indistinguishable by a simple algorithm, efficient algorithm. So for any K not scaling with N. Then the outer wedges are actually identical, meaning that the distance between the bulk states restricted to the outer wedge. These are the duals to these. This is strict to 0. Now here we're working again with this, there's no n in the bulk because we're working with the QFT on a curved background. So we're not, any subleading and n corrections are going to be 0 for us in this construction.
The large and limit.
Sorry?
This statement is true in the large and limit.
This statement is true in the large and limit. Yeah, in the bulk, we don't have n anymore. We just have QFT on a curved background.
And this distance is not a computational. This is like for anything you could do.
So this is just, sorry, this, you know.
Like that means
So
that
this is the one norm distance for any state that satisfy this requirement.
one norm meaning you can do anything.
All right, now, this is very closely related to something that's already been defined in the CS literature known as EFIs. It's a slightly stronger notion of EFIs, so. First, I'm going to talk briefly about EFIs, and then I'm going to go through the argument for why this is true. All right, so EFIs, 5 pairs. So EFIs are efficiently comparable far apart indistinguishable pairs. And the usual definition, so this is
Sorry,
Persky et al.
I have a good question. So what do you allow K scale with n, but sample with linear?
No, K is not, K is constant with respect to n.
Oh, K is cubic
This is
feet.
not, there's no n dependence. K is anything you want, but it's just gonna be a scalar.
Okay.
Yeah. Alright, so EFI pairs are, I'm gonna define this all on the boundary. So this is mixed, efficiently comparable states on Hn. And we're going to assume that log the dimensionality of this scales polynomially with n. So these constitute what's called an EFI pair. EFI. If first we have this requirement of the distance between them is greater than 1 over poly n. Rho n and sigma n are a single completely indistinguishable, but you are allowed advice. And as I said, they are efficiently comparable. So these are what's known as EFI states, EFI pairs. And this, you don't see entanglement coming up here. This is far apart in this sense. But of course, if you have two states with a very large difference in entanglement, then they'll also have a very large distance in this case. So EFIs and entanglements are a little bit more general than just something that spoofs entanglement, but they do also encompass entanglement spoofing. Now, for us, this is not quite good enough because we want these things to be far apart in a way that survives the large n limit. So we're going to strengthen this a little bit to something that we call large n EFI pairs. And we're going to make this be, these have to be something greater than or equal to something that doesn't go to 0 in the large n limit. So this is the number, which is not, does not vanish. Large n. And we're going to also allow them to be actually multi-copy. Copy indistinguishable. And what we're going to argue is that EFI pairs essentially fall under we are able to apply this main result to EFI pairs and show that whenever you have an EFI pair, it's large n EFI pair, at least one of the states has a Python sludge in the bulk dual.
So, sorry, here is you improving their theorem or it's a stronger assumption?
So
for the-
there's
for
a
the
stronger
one.
assumption here, which is that I'm requiring the distance between these to be larger than is required in the usual construction or in the usual definition.
This
So
is
certainly
this-
anything which is a large NEF5 pair is also an EF5 pair.
Oh, okay. But this is assumption, this start, so
It's not an assumption, it's a definition.
a definition, okay, okay.
It's just a definition.
The definition is somewhat like saying that rho n and sigma n can be distinguished abstractly, although not efficiently.
Well, I mean, it just because they have large traits doesn't mean that they can be distinguished. I mean, if you have an exponentially complex algorithm, yes. But the whole point, I mean, they have to be, they're multi-copy indistinguishable, so they do have to satisfy that requirement.
To some extent that they are defined to spoof entanglement. Is that?
Yeah, so I mean, these are essentially very nice entanglement spoofers.
Yeah.
They're, it's single state, you don't have to worry about ensembles like we do with pseudo entanglement, which is sort of a more standard term. And at the same time, they do roughly exactly what we want them to do. And as we'll see, they follow the same pattern as the Python's lunch, as the evaporating black hole in terms of having a Python's lunch in the less entangled state.
Is there still going to be a statement about the difference between the von Neumann entities between it?
So it will not turn into a statement about the difference between the von Neumann entropies, simply because this is a more general statement. If you have a large difference between the von Neumann entropies, you're going to have this distance would be large. So this is, in some sense, this encompasses more than that. This is really about indistinguishability and being far apart in a more general sense.
So this does not imply that these are entanglement spoofers.
So not all states like this will necessarily be entanglement spoofers, but if you have entanglement spoofers, they will satisfy.
So what did you wrote? The number does not what?
Number that doesn't vanish at large.
Does not vanish.
Also, I mean, okay, I'm not gonna get, there's an asymptotic notation for this that I'm just gonna try not to get into if I possibly can. Okay, so so I'm going to now argue for this main result. So basically, if you have multi-copy indistinguishability and these are geometric states, then their outer wedges, the outer wedges are identical. And from there, we're going to find that EFI pairs always have a Python's lunch in at least one of the states in the lower entangled state, and the state with the lower rank. All right, so you have enough time for sketch variant. So the way we do this is by the contrapositive. So we assume that the distance is strictly not zero. And that means that there exist operators that essentially distinguish between these two. So quantitatively, the expectation, there exist operators with different expectation values. For any epsilon, it is possible to find an opposite for all epsilon there exists in O that satisfies this equation here, where this is the operator norm. And this is a bulk statement, but we can translate it to a boundary statement using the fact that our states are related to, both boundary states and operators are related to one another via quantum channels.
So here, all the O you choose are in this outer wedge or algebra, right?
These are, sorry, one more
Yeah,
time.
what's the O? The O are in the outer wedge algebra or in the full algebra?
So O will live in the outer wedge algebra, that's right.
Okay, O is always in the outer wedge, okay.
That's right, because here we assume that the distance in the outer wedge is not.
Okay,
Yeah.
okay.
So we can translate this into a statement about the boundary. We can try to go through as little of the calculation as possible, while still being illustrative. And this turns out to be given by the variances of the operator
So
in the different states.
D is the dimension of the Hilbert space.
I'm sorry,
What is the D?
D is this quantity here.
Oh, okay.
That's the distance in the outer wedge. This is multiplied by D minus epsilon. And some function that goes to, that is positive function and goes to zero and goes to infinity limit. Now, it turns out that this statement implies that the states cannot be multi-copy indistinguishable. And there's a bunch of algebra that you need to do to get there. And since I'm starting to come up to be a little bit short on time, given that I want to talk about pseudo entanglement, I'm not going to talk about the algebra that you need in order to get there. But the idea, let's see if this thing I need. The idea that we imagine taking an operator that measures, so we have an algorithm. And the algorithm is going to measure ON some k number of times. It doesn't scale with n. Now ON is simple. As long as k that is not super polynomial in n, then we can just measure it as many times as that many times, and this is a simple algorithm, a simple operator, it can be done. So from this, we get a measurement outcome. We can average over all of the outcomes of measuring ON in each of these two states, sigma n and rho n, and we get a measurement outcome out of that. Now, the measurement outcome allows the algorithm to create a test, which it can use to decide if the state is sigma n or rho n. So in particular, if the, let's see, all right, I'm going to skip the actual test itself. But the idea is that the algorithm can execute a test. So the algorithm it uses the measurement outcome to create a test. The test allows it to determine with some probability whether it's rho n or sigma n. And we can compute the probability of the algorithm being wrong. For the states to be indistinguishable, we want the probability of being wrong to be greater than a half. For the states if the states are not indistinguishable, the probability is going to be less than a half. So we find that the probability of the algorithm being wrong, remember we're doing this by the contrapositive, so we assume the distance is not zero. We want to find that the probability of that the states are actually distinguishable. They're not indistinguishable. So the probability of the algorithm being wrong is less than a half if the number of copies of the state that you get, so the number of times you can measure this O, is greater than 4 over d squared in the large n limit. So as long as, since we assume d is not equal to 0, so as long as d is not equal to 0, then there exists some k where the probability of the algorithm being wrong is less than a half, meaning the states are distinguishable for some k that does not scale with n. And that tells us that this means that the states are distinguishable with high probability. Or multi-copy distinguishable.
Still for large enough K.
Sorry?
For large enough K, yeah.
Yes, that's right. For large enough k that does not have to scale with n. And this is the proof that we wanted. So d is not equal to 0 means the states are multi-copy distinguishable. So by the contrapositive, if the states being indistinguishable means that d is equal to 0. And that proves this main result. If we have multi-copy indistinguishable states, then we have identical outer wedges.
Here, where did you use, there's a geometric state? I can just consider any sub-algebra of the algebra called like a outer wedge and do this test.
Why do I need geometric? Well, if I don't have
Yeah.
geometric states, I don't have a bulk. And then I don't have anything that like rho
So
or
I just,
sigma, I don't know what.
Maybe I just want to understand like why the special outer wedge is very special in this
So that's what allows us
just
to
show the
say
random
that there exists,
sub-algebra?
that's what allows us to say that there exists a simple algorithm that can execute this task. Because ON is simple if and only if it is dual to an operator that lives in the outer wedge, in the outer wedge algebra. Okay. So applying this to larger and EFI states, the application is essentially immediate. These are multi-copy indistinguishable. That tells us that the outer wedges of the states are identical, but the states are far apart, right? They're far apart in a way that does not go to 0 as n goes to infinity. And that means that the entanglement wedges of the states have to be different. The outer wedges are identical, the entanglement wedges are different. And this theorem tells us that that means that there must be a Python's lunch in at least one of them. So,
Although the geometry of, the difference in the geometry of the entanglement wedge refers to a difference in the von Neumann entropy.
yeah, so it does mean that there is a difference in the von Neumann entropies, but we can't just using this parameterize or tell you how large that difference is. It can't be, I mean, it can't be order 1. It has to be more than that. But we can't tell you how large the gap is between them.
Which means you cannot tell the geometry of the two.
But I cannot tell you what the geometry looks like. All I can tell you is that at least one of them has a bulge. And it has to be the one with lower rank that you can show. So large N EFIs have a Python's lunch in one of the states.
At least one, right?
At least one, that's right, yeah.
Could you say again, what one implied, that doesn't have to imply that they have different extremal surfaces.
Doesn't what, sorry?
Doesn't have to imply that they have different extremals, QASs. Like number 1 of the EFI.
Number 1, where have we used it? Is that what you're asking? I mean, we need the fact that they are far apart
just
so that
misheard.
their states are actually different and in the large end limit.
Yeah,
If they're not different in the large end limit, we don't know that the entanglement wedges are different, and then it could just be the same entanglement wedge. And then all we say is the outer wedge is identical, the entanglement wedge is identical, and it doesn't mean that there's anything behind the outer wedge.
yeah, this is the part that that went too fast for me. But yeah, so if I have 2 states, like I can make them very different even if they have the same entanglement wedge.
No,
Yeah, I mean, I just put a qubit in the up state and a qubit in the down state, then
good.
they have, distance.
So,
Massive.
how do I say this? This isn't, okay, so here we are working with by assuming that these are different states in a way that survives in the infinite and limit. We are, in some sense we are, okay, so this is an assumption that I didn't state explicitly that I can state in more detail later, that the geometries are gonna have to be different if they differ at large n. So this is folded a little bit into the way we make this assumption over here, but I didn't say it in explicit detail. So let me, I mean, it's a technical question, it's a good question, but I want to move on a little bit to the pseudo entanglement. I'm happy to answer questions afterwards. It sort of gets folded into this over here. Yeah. Okay.
But the EFI generally, it does not need to be geometric state, so this.
Definitely not. This is, I mean, but we only care about.
You just
states that
use
are
the
geometric.
condition, it's a multi-copy indistinguishable, then you just connect to,
I mean, we care about geometric states primarily because, well, if we're just talking about EFIs but that are not geometric, then what are we, I mean, holography just doesn't apply. So we want to ask what is the gravitational manifestation of these, and so we need them to be geometric states. So that's just an assumption that we can do this in holography. The things that we actually strengthened are this large n business and the multi-copy. Yeah. Okay, so I think I'm supposed to finish by 12:30 the absolute latest.
So, I guess.
Oh, okay. I see. In that case,
Maybe we could make a break
let me-
and people can leave, we'll have to leave and then.
let me see if I can summarize. Let me say I'm just gonna say a few words about pseudo entanglement and then I'll wrap up. So pseudo entanglement is something which has been discussed a lot recently in the CS literature as another construction, which is actually explicitly entanglement spoofing. Instead of referring to this trace distance here, we're actually referring to the value of the entanglement, the von Neumann entropy. So the way that this is normally done is you construct 2 ensembles, right, just a little bit. You construct 2 ensembles of states. And the idea that across some bipartition, one of them is very highly entangled, the other is very lowly entangled across that bipartition. But when you draw from the ensembles, on average, what you find is that with high probability, rather, what you find is that these are indistinguishable from one another. And the way that indistinguishability is framed is in terms of the average state. So what is normally done is you say, okay, you take the average state, which, with some normalization, goes as the sum. So now I'm going through this notation. So they consider this average state with some normalization up here in terms of the index for each one of these, and they say, okay, this is one copy indistinguishable from this one. And if you want multiple copies, then you take tensor product here and you say these are n copy indistinguishable. Now, the issue is, of course, that this is different from this notion of a multi-copy indistinguishability, because here you had multi-copy indistinguishability of the states. And here, it's not that we have multi-copy indistinguishability of the average, is that we have, if you average more states, then they're still indistinguishable. So we actually can't directly use this result here to prove that we have a Python's lunch for pseudo-entangled ensembles. Instead, we have to go through a different route. But the upshot is essentially the same. The upshot is that there exists a Python's lunch in the average state of the pseudo-entangled ensemble for the lower entanglement state. So I'm just going to write down the result here. There exists a Python's lunch in the average state. So these two different notions of distinguishability, different notions of entanglement spoofing, together both of them have Python's lunches in the dual, which suggests that indistinguishability, even if it comes in different kinds of forms, and entanglement spoofing is in some sense always has the same avatar of the Python's lunch. Now, I started this talk with 3 questions. So I just want to address those, and then I promise I will finish. So the first question that I asked is about the evolution. What kind of evolution can generate entanglement spoofing states from non-entanglement spoofing states? And it's an interesting question, and one that I can't definitively answer at present. But we can ask, what kind of we can talk about the connection to pseudo-randomness. So in the pseudo-entanglement paper here, the way that they constructed the pseudo-entangled ensembles was using pseudo-random ensembles. And in a recent paper with the same group of co-authors, we found a close connection between the formation of black holes and pseudo-random unitary dynamics. Now, we don't expect that pseudo-randomness is necessary for pseudo-entanglement, but there does appear to be a very close connection between the two. And so the question is, is pseudo-entanglement going to give us a clue as to what is a better model for black hole evaporation, for black hole evolution, than the pseudo-random unitaries, which are already pretty good? And as to that, I don't have an answer, but I think it's a very interesting question. Now, the second question I have a somewhat more satisfactory answer to. So the second question was about uniqueness. Are black holes the only gravitational sources of entanglement spoofing? And at least, if by entanglement spoofing, we mean multi-copy indistinguishability between states that are very different, then the answer is, well, there's always going to be a Python's lunch. And you can prove, even without assuming global hyperbolicity, actually, you can actually argue that a Python's lunch always has to lie behind the horizon of a black hole. And so that means that as long as the link between spoofing entanglement and multi-copy indistinguishability, and therefore Python's lunch is robust, then yes, black holes are the only systems, the only gravitational phenomena that can generate entanglement spoofing. And now the final question was whether fake entanglement can actually build something for us. And it does look like fake entanglement creates this space-time, this Python's lunch, space-time that has to be behind the outermost QES, because the outer wedges are identical, but the entanglement wedges are not. So having entanglement spoofing means that you can't build a full bridge, but you can kind of build a little bit of extra space-time behind the outermost QES. So apologies for the rushed ending. I am running out of time, so I'll stop there. Thank you. Any more questions?
Oh, I have a question related to what you talk about the uniqueness of a black hole, the source of the spoofing. So here, so I think everywhere you just assume there is some geometric, the states are geometric, so that's why you talk about Python slot, right?
Yes.
But if we define Python slot just as like an indistinguishable and the binomial entropy difference, could we just say that's Python slot? I mean, in that sense, even though I have some state which is not geometric state, but I think you can still find something like a spoofing, right?
I mean, if you just define Python's lunch as spoofing, then by definition, spoofing will be a Python's lunch.
Right,
But
but
of
there
course,
is,
what we really want is the geometric avatar, of entanglement spoofing. I mean, if you, again, as when I started this talk, I said I'm a high energy theorist and I care about what gravity does with this.
yeah,
And that means that I care about what the geometric states look like. I don't care what the non-geometric states look like because, well, I care about gravity.
okay.
Yeah, Douglas.
What is the one norm for the density matrix restricted to that algebra? How is that defined?
Yeah, so this thing here, so this is just the restriction of, are you asking about what is this restriction, or are you asking about what is the one norm? I mean, this is just literally, this is just the reduced density matrix in the bulk. So this is the bulk statement here. This is the reduced density matrix in the bulk on the outer wedge.
But then I thought it was like isn't it a standard fact that the one norm determines the distinguishability of two states?
So it depends on what kind of, so if the one norm determined distinguishability of the states, then you wouldn't have things like EFI.
Well, no, but this is the one norm of the like state in the part that you're allowed to look at, the outer algebra, which is the simple
So
computationally accessible.
you're saying,
operator.
doesn't this tell you that these two states are identical on the outer wedge? Yes.
Yes.
It does.
Yes.
And
I mean, this is a consequence of indistinguishability, of computational indistinguishability.
right, but I'm trying to, so
If I had started by saying the outer wedges are identical, therefore that would be kind of tautological. But I'm not starting with that. I'm starting with a statement about
isn't that a
indistinguishability.
standard thing, that one norm is equivalent to indistinguishability?
So this is not equivalent because we don't have a converse. But what we have here is that for this particular notion of the K-copy computational indistinguishability, for this particular K, you can prove that the one norm, this gives you that they're identical with respect to the one norm. In fact, if you try to prove it for single copy indistinguishability, we actually came across what looked like a likely counterexample.
Is the computational restriction, does it equivalent to saying you're allowed to measure anything in the outer algebra?
So the computational restriction, so it's one that's intuitive, in the sense that you say, oh, if I can reconstruct the outer wedge from simple operators, then that means that, this kind of has to be true because these are computationally indistinguishable. It turns out to be relatively non-trivial to prove it, and in particular, because for one single copy indistinguishability, this does not appear to be true. So it actually is kind of important that what you mean when you say distinguishability and what kind of what you have access to. So there are a number of subtleties in going from this to that, which requires to have this particular notion of indistinguishability. I mean, the intuition is correct. Indistinguishability should imply that, but what kind of indistinguishability is a little bit more subtle?
I mean, K-copy access to the outer wedge, is that equivalent to? It seems like you get to define what you mean by computationally indistinguishable in this case.
Yeah, so computationally indistinguishable, what I mean here is that there does not exist a polynomially complex algorithm that can take K copies for any K that does not scale with N, can take K copies of these states and tell that they're not the same state.
And you're not assuming that means that they are accessing the outer wedge.
No, I'm not assuming. I mean, the only assumption I'm making is that if the algorithm is simple, then it is allowed to compute simple operators and expectation values thereof.
But let's see, if we didn't know,
So I think you're.
how do we know those simple things couldn't go beyond the outer wedge?
So what prevents you from doing that is the operators are no longer going to be simple, so you can't rely on your algorithm being able to compute
But
them.
how, let's see, but that's some input, right? The simple
Yeah,
operators are.
so it is
defined
input that
things
the
in
simple
outer
operators
wedge.
live in the outer wedge algebra. I think what you're expressing is the expectation that this should be true, simply because we say, well, these operators are simple, so it should be computationally indistinguishable to tell the difference. Now, what I'm telling you is that intuition is correct, but there's a caveat here, which is number of copies. So otherwise you can sort of, the intuition is correct, but otherwise you can find loopholes in the reasoning.
Well, I think that number of copies issue arises in the standard discussion of the one norm and state indistinguishability. If the one norm is non-zero but small, then you need many experiments to distinguish the two states.
Yeah, so I mean, so you can relate, literally, this is the relation between the probability of the algorithm being wrong. And again, this is a probability, it's not like one, you know, we're talking about being, or zero, we're talking about being less than a half. And what we find is, you know, this bound on K, and of course, the larger D is, the smaller your K could be.
So far, your story is completely general. Could you give me a concrete example to help me better understand this new concept?
This new concept, which new concept?
Well, you like the Python lunch and the spoofing entanglement. Can you consider the actual system that satisfy this assumption you introduce and do this algorithm to repeat the story?
So, I mean, if you're asking for what the takeaway is,
I want to have better understand why you have this assumption. Your intuition had.
oh, you mean why would we take EFI pairs, why would we modify the EFI pair definition to a large N EFI pair?
Yeah, I don't know how to.
Yeah, so we've motivated this basically by saying we want to have a geometric description, we want to understand a geometric description of entanglement spoofing. The original definition did not lend itself to that. For example, we couldn't take the large N limit in a way that would ensure these states remain distinct. So that's one thing that we absolutely had to modify in the definition. If we're going to have a dual geometry, it's going to be a sharply defined geometry. We need to be able to take the large N limit, and we need the content of the definition, for example, the far apart piece, to remain robust in the large N limit, which this did not have that. This did not have that property. So we modified the definitions in order to be more amenable to applying it to a gravitational system. Otherwise, in some sense, the far apart piece just goes away. States don't have to be far apart, and then it's kind of trivial. Then the whole thing kind of becomes a little trivial.
So basically, do you have explicit construction from qubit for the EFI pairs?
An
A
explicit
large
construction.
in EFI pairs.
I mean, I wouldn't say we have a construction of those. For pseudo entanglement, there is a candidate construction in ADS CFT, which is a modification, a slight modification of the VFB, Bullen-Maserati construction. So there's a candidate construction, and it does in fact have a Python sludge in the average state. For EFI pairs, we don't have a construction. We just say that, if you have an EFI pair, a large EFI pair, then you end up having a Python sludge.
But it's good in there are constructions, many constructions of EFI pairs on the
Yes.
center.
Yeah, but as far as I know, not these large N EFI pairs.
Yeah, they
Oh, I
need
see.
to change the first, I think the first condition is really crucial because if they really want, they have a
Large-
big difference. The condition one.
Yeah.
Whereas you still have indistinguishability. This is very different from original definition and probably.
It's not that
I
different.
think you can have rho n and sigma n actually have maybe I should put it offline. I think you can have large systems, you take a post-quantum secure classical commitment, I think this would give you both properties.
If you both properties,
Yeah,
okay,
I
then
think
that would be,
that's-
that would be exactly the kind of thing we're interested in, if you can argue that it has a semi-classical bulk description.
That I don't know about.
Okay.
One last question.
Right, yeah.
Thank you. What does this story tell us about the black hole evaporation? Does it tell us that somehow we can reconstruct the Python launch or?
Well, we could, so we didn't need the story to tell us that we can reconstruct the black hole interior. That's in some sense old news from 2019. But the potential that it has to shed light on the black hole evaporation process is in understanding better the way that entanglement spoofing works in gravity. So we can ask questions like, what kind of unitary operators have the property that they can take a state which is not entanglement spoofing and generate a state which is entanglement spoofing. And that gives us some control or some understanding of what the dynamics of black hole evaporation have, the properties that has to satisfy. So that's an example of something we could learn from this story. We're not, this is not there yet. This is kind of beginning of an investigation into what does entanglement spoofing look like. But it does give us some understanding that this is a very unique process that we probably don't have an analog of this aspect of the information problem in other gravitational systems, because black holes appear to be the only things that can spoof entanglement.
Okay, thank you.